Hey guys, today we'll be talking all about Nicholas Copernicus and his really important contributions to astronomy. This is a lesson that it'd be good to have a calculator with you to go through some of this math together. Nicholas Copernicus, very famous for being the first guy in more or less modern times to bring back the heliocentric model in the 1500s. This is a really important contribution he makes. He does a real good job trying to explain that weird retrograde motion that planets do. He finds the length of the year on planets and even finds the distances to that. He's able to explain why Mercury and Venus have the kinds of motion they do through his heliocentric model. Literally for 1500 years before him, we're using Ptolemy's weird epicycles and deference system because it works. It's not until Copernicus that we start to get rid of that. So under Copernicus's model, if all the planets are going around the sun, when the planets pass by each other, this is going to be why we see that retrograde motion. A good analogy to today is if you think about if you're stopped at a stoplight or if you're driving on the highway, as you pass another car, when you look at them, it almost looks like they're moving backwards. You know they're not, but that relative motion of you passing by them makes them appear to move backwards. And so in this setup, as the Earth passes by Mars, that explains why Mars seems to move backwards. So some important things we got to cover first before we go on. How Copernicus would describe where he believes the planets are in the solar system, these different planetary positions. So here you can see we have the sun at the middle. Here's the Earth right here. This is the Earth's orbit. This orbit and the planet at these positions, this is what Copernicus calls a superior planet. It's further away from the sun than the Earth is. And so here, this planet, this is an inferior planet. Mercury and Venus, it's closer to the sun than we are. So Copernicus describes this position as opposition. It's on the opposite side of the sky from the sun. So this is kind of like the full moon is in opposition to the sun from the view of the Earth. Over on the other side, this is what we call conjunction, where from the view of the Earth, the sun and the planet are perfectly aligned. This is conjunction. Over here is opposition. Then we have these other two positions. Notice how right here these lines intersect at 90-degree angles. So he calls this over here eastern quadrature, and this is western quadrature. Remember, in a view of the sky, east and west are flip-flopped, but here you can think of as different quadrants, eastern quadrature, western quadrature, when the planet is at a 90-degree angle to the sun. So those are the four positions that a superior planet can have. For an inferior planet, we have right here what he calls inferior conjunction. Notice that's when the planet is between us and the sun. Over here, he calls this superior conjunction, when it's on the far side of the sun. Notice both of these are only going to happen with an inferior planet. So an inferior planet can be inferior or superior conjunction, whereas a superior planet can only be in conjunction. And then we have, notice this is a 90-degree angle. This he calls the greatest eastern elongation, and over here the greatest western elongation. They can never appear further away from the sun than when they are at this greatest elongation. A superior planet, notice its greatest elongation is at opposition, 180 degrees away from the sun. So another way to look at that, if this is the Earth, here we have an inferior planet. So right now it's in inferior conjunction. It moves along. We go over to greatest western elongation. It moves along. We don't care about these positions. Hey, look, it's in superior conjunction. Moves along, moves along. Now it's over to greatest eastern elongation. And now it's back to inferior conjunction. Now if we move the Earth right here, and now we have a superior planet out here. Right now it's in opposition. Well, now it moves out to western quadrature, moves along, moves along, moves along. Hey, it's in conjunction, moves along some more, eastern quadrature, and now back to opposition. So Ptolemy, he talks about the synodic period of a planet, the time between two conjunctions. Technically, it could be the time between two oppositions or two greatest western elongations, but it's essentially the time that it takes for a planet to get from one position, move through its cycle to get to that same back basic position. But we know now, because of Copernicus, the Earth is also moving. So we're going to say the synodic period of the planet is S. The period that the Earth takes to go around the sun, that's E. What we want to know is the true sidereal period, what we're going to call P, the time to take for that planet to make one orbit. But because we can't go to that planet, we can't measure that directly. So we're not going to worry too much about how he gets the math for this. We'll tackle that in a different video. All we need to know for right now is that he determines this equation to determine the sidereal period. 1 over P, the sidereal period, equals 1 over E, the Earth period, minus 1 over S, the synodic period. Now this is only going to work for superior planets, like Mars, Jupiter, and Saturn. For inferior planets, it's a little different. 1 over P equals 1 over E plus 1 over S. So let's practice this a little bit. Here we've got the synodic period for all the planets. Mercury, Venus are two inferior planets. Mars, Jupiter, Saturn, Uranus, Neptune, Pluto for all of our superior planets. So let's determine the sidereal period for Venus. First off, we got to remember Venus is inferior. So we're going to need 1 over P equals 1 over E plus 1 over S. So let's write this down. 1 over P equals 1 over the Earth period, 365.25 days, plus 1 over 584, the synodic period for Venus. So this is going to be fairly easy as is to put in your calculator. 1 over 365.25 plus 1 over 584. You should get something like this. 1 over P equals 0.00445. Now, this is only 1 over P. This is not our answer. So I want to point out something really important. If you got a scientific calculator, there's a good chance you have a button like this. 1 over X. Maybe it says X to the negative 1. This is going to make fixing this very, very simple. But we need to take 1 divided by this to get our answer. So we can just have this number. We can hit 1 over X, or we can hit that X to the negative 1 button, and we should get a sidereal period of 224.7 days. If you're using Desmos, it's not going to be so simple. There's unfortunately not a button here, so let's take a look at how we do that. So let's try this on Desmos real quick. If we have 1 over 365.25 plus 1 over 584, notice that gives us our 0.00445. So I can always click enter and then click answer. Click this button to raise it to the negative first power, and there's my answer, 224.7 days. So let's now try to figure out the sidereal period for Mars. So we have to remember that Mars is a superior planet. Its synodic period is 780 days. So let's write down our equation. 1 over P equals 1 over E minus 1 over S. And let's start filling in what we know. 1 over P equals 1 over the Earth period, 365.25, minus 1 over 780. You should find that 1 over P equals 0.001456. Now remember, this is not your answer. That's 1 over P. So we need to take this, we need to take 1 divided by this number, or take this and raise it to the negative 1. If we use those buttons, we find the sidereal period of Mars, 686.8 days. A lot longer because Mars is further away from the sun than we are. An interesting thing to look at, if you notice, going from Mars to Jupiter, Saturn, Uranus, Neptune, Pluto, notice what happens to the synodic period as you get further and further away. Wonder what number we're heading out to and why that might be. Now, in Copernicus's time, we have no idea how far away the Earth is from the sun. But to Copernicus, who cares? We're just going to make up a unit of measurement and call that the astronomical unit, or 1 AU, the distance between the sun and the Earth. Now we know that that's roughly 150 million kilometers between us, but back in his time, we had no real good way to know that, and in fact, who cares? We're just going to set everything in terms of the AU, the Earth-Sun distance. So now that Copernicus has figured out the sidereal time on these different planets, he can figure out the distance to these planets. So an inferior planet is actually pretty darn simple. He knows that the greatest elongation of Venus, either east or west, is right about 46 degrees. So if we draw out what that looks like, here's the Earth, here's Venus and the Sun. At greatest elongation, notice there's a 90-degree angle here. He knows that Venus can never be more than 46 degrees away from the sun. So notice we have this nice, perfect right triangle here. We've declared that the Earth-Sun distance is 1 AU, so we're not interested in the Earth-Venus distance, we just want to know the Venus-Sun distance. That's the D that we're going to solve for. So notice if we have this angle, here's our opposite side, here's our hypotenuse, we want sine. Sine of the angle equals opposite over hypotenuse, which is D over 1 AU. Notice that's just going to go away. So literally all we have to do is the sine of 46 degrees, 0.719. Venus is right about 0.72 astronomical units away from the sun. That's less than 1 because it's closer to the sun than we are. Now, finding the distance to a superior planet is going to be noticeably more challenging because where is the greatest elongation a superior planet can have? It's in opposition. There's no triangle there whatsoever. So what we're looking for here, we know that at some point in time, the Earth, the planet, and the sun are lined up. The planet's in opposition, and over time, the Earth's going to move more, but the other planet's still going to move. And hey, eventually, we're going to get out here to quadrature, where we have a right triangle. Now, it would be great if we had this angle here, but the only way to get that is to literally be on the surface of the sun, which is kind of impossible, so we don't know this angle. But Copernicus has a trick up his sleeve. Now, because we know how long the superior planet has traveled, and we know how long its year is, we're going to be able to figure out this angle right here, we're going to call S, and remember, same basic thing, we know how long the Earth has traveled from this point to this point, so we're going to be able to figure out this angle that we're going to call E. The Earth goes 360 degrees around the sun in 365 days, so the difference between these two angles, E and S, this is going to give us the angle A that we want. So, to find the distance to a superior planet, first step, we're going to find the time from opposition to quadrature. We're going to divide that time by the sidereal, the true year for each planet, multiply both by 360. That's going to give us an angle for each planet. We'll find the difference between them. That's going to give us a triangle, and we'll solve it, and we'll have that distance. So let's try this with Mars. So, if, for instance, Mars is in opposition on March 3rd, where we have this set up right here, 97 days later, it's in quadrature, this setup right here. So what is the angle that the Earth has traveled? Well, we took 97 days out of our 365-day-long year, 97 divided by 365, multiply that by 360 degrees. That means the Earth has traveled 95.7 degrees around the sun in this time. How about Mars? It also went 97 days, but its year is 687 days. So 97 divided by 687 times the 360 degrees of a circle, Mars has only traveled 50.8 degrees in the same time we went 95.7 degrees. So the difference between 95.7 and 50.8, that's 44.9. That is this angle right here, the angle that we can't directly measure because we don't live on the sun. But notice now we have a triangle we can solve. We know that the Earth is 1 AU from the sun. We want to know how far Mars is from the sun. So notice we have the hypotenuse of our triangle and the adjacent. So we have cosine. Cosine of 44.9 is equal to the adjacent over the hypotenuse, 1 over x. Notice this is going to be a little bit weird to solve. So x times cosine of 44.9 equals 1 AU, or the distance equals 1 over the cosine of 44.9 degrees. So we should find that Mars is 1.4 AU from the sun. So there we go. With Copernicus, we have really got a solid foundation now for the heliocentric universe with the sun at the center. The Earth is no longer just some mysterious orb. We are, in fact, the third planet around the sun. Now, you might have heard people don't necessarily take to Copernicus's model right away. And while some of that might be for various weird reasons, what we're going to find is Copernicus's model was actually less accurate than Ptolemy's weird epicycles. We'll see why when we start talking about Kepler and what he brings to the table. But there's actually a really good reason people aren't going to go over to Copernicus's model right away.